So can someone sum up what we have actually learned in the previous lecture? Some of you I remember being. Some of you are new, but some of you. So what did we do? Okay, let's see. I'll have a discussion with myself. We said that in quantum mechanics, well, we started with classical mechanics. Classical mechanics, we have a particle, we define 6 numbers, its position x, y, z, its momentum px, py, pz, and if we know what are the forces acting on it, we can calculate everything that will happen to this particle at future time. Okay. We can't play this game in quantum mechanics. I didn't go into why can't we play. Actually, no one can go into why can't we play, but it's an experimental fact. People for 25 years tried to write down something that will give them a similar behavior and weren't able to do it. So they came up with new concepts for describing physical measurements, and that was the wave function, which I claimed, or they claimed, contains all physical information about the system we are interested in. We said that this wave function has to fulfill some conditions. For example, if we square it, we are getting the probability of finding the particle anywhere in the system. And since the probability has to sum up to 1, the integration of the square of the wave function has to be equal to 1, for example. And we met how to extract physical information out of the wave function. We met a few operators: position, energy, momentum. And we wrote down our recipe how to calculate averages of these quantities out of the wave function. Okay, what will we do today? We'll do, hopefully, the first half, 2/3 of the lecture will be just seeing that these averages actually behave as expected from classical physics. Not that they are classical physics, they're completely different, but the averages fulfill laws that we can recognize out of classical mechanics. For example, Newton's law. Then we'll do a refresher course on linear algebra. Why? Basically because all the mathematical infrastructure of quantum mechanics is linear algebra. And I know that all of you have taken a course in linear algebra, but from my experience, some of you don't remember it. Some of you can prove all kinds of stuff but not do a calculation and will need to do a calculation. And some of you have strange views about the concepts that appear there. And I want all of you to be on the same page when we are doing whatever we need to do in this course. Okay, so let's start. Newton's law. The acceleration of a particle times its mass is equal to the force acting on the particle, or if you want, the particle is accelerated by a force that is applied. Okay. Okay, I just rewrote it according to the definition of what is acceleration. Can I start here?
Start what?
Start the calculation here.
What would you say the force is?
Okay, what is the force and what is V? Both of them we haven't yet defined in our famous dictionary of operators. But with a bit of change of notation, I can write down exactly this equation according to the dictionaries that we have met. The gradient of the potential is the force. Okay, and potential we defined. Momentum we have defined. Okay, so life is good. We can at least start doing something. Okay, so what do I want to prove? I said I want to prove these quantities for averages of a that we get for any wave function. Okay, we haven't yet introduced the notation. Just wrote how I'm calculating averages, as we have learned in the previous lecture. Nothing more, nothing less. What do I know about psi?
Can be complex.
It's a complex function, and it's normalizable. These are the two quantities I know about it, two properties. What is the specific psi? Depends on the system, which we haven't defined. But I want to show it in general, not necessarily for a given system, but in general, give me a kosher wave function, should follow these rules. Okay, so let's see how we move. I want to start actually with a pre-step. Okay, that's a definition actually. But since I introduced my operators as a dictionary, I would like to get a feeling, is it correct? And remember, when I put this hat on any quantity, it means the operator. In a moment, I'll write it down specifically. Okay, I'm working with the definitions of the operators and how do I calculate an average. That's all, nothing more. Okay. Just to make life clearer, these are actually three equations. Because I have average of x, average of y, average of z, average of px, average of py, average of pz. So I'll write it down explicitly, at least for one of the components. Why am I allowed to exchange the position of psi x here and not the derivative here?
That's multiplication.
Excuse me? No, I just didn't hear you.
Sorry. You're allowed to switch the multiplication on the right side,
Mm-hmm.
and on the left side, you need to do the derivative, and that could change.
Exactly, because exchanging here psi and the derivative is just mathematically incorrect. On the other hand, a simple multiplication, I'm allowed to exchange. Okay. This is our good old friend, the density, right? Psi squared. So, just not to fill up the whiteboard in trivial statements, the same I can write down for y and z. Okay, I have three equations here. Can put the derivative inside. And since x doesn't depend on t, explicitly I'm allowed to move it before the derivative. Here everything stays the same. Okay. This guy we have met previously. What is it? Don't be afraid to speak. People speak nonsense all the time. It doesn't hurt you. Please start it. Yeah. What's your name?
It's how it's called? The function.
In Hebrew? You know how it's called in Hebrew, or just you don't know the name? It's a problem in English or in naming?
In naming, it's like the
Mishvat HaRetzef, the continuity equation, which we met in the previous lecture, and we have seen it on the whiteboard when we entered here a few moments ago. Okay, so let's have a quick refresher on the continuity equation. Use this corner. Which the basic idea behind it is if I'm looking locally on what happens to the density, the only way that the density can change, which is the derivative according to time, is that we have some current coming in or going out of this region. We turned it into an infinitesimal point here, so that's a continuation equation. Okay, so I'm continuing with the right-hand side. And I left the minus out of the continuation equation. What did I do here? Someone has an idea? took this part, wrote down the continuation equation. So I should have here x times minus gradient of j, the divergence of j. And what did I do? I just pulled it before. And derivative of x is equal 1. So I subtracted. So minus, so this is in plus. So a small mathematical manipulation of the equation. Last manipulation, Gauss laws. Someone can explain why this is 0? Let's go a step back. And what is the integration on R? And what is the integration over R? Excuse me?
X, Y, Z.
Of course, but what is the volume that I'm integrating?
Sphere?
The whole world. The whole space. So, the surface that I'm writing down here in Gauss's law, encompasses the whole universe, basically. What is the current at the edge of the universe?
0.
0. Must be 0 because you can't leave. You're somewhere in space. Please. It's almost by definition. Okay, why? Because I said that the wave function is normalizable, right? Wherever I integrate over the whole volume, I get 1. Now, if I have current out of it, I don't have 1, because I have current out of it. Of course, if you take part of the universe, could be that we have current, the density within this volume can change. Not when I'm encompassing the whole universe. Okay, so I did here a very long exercise. And change colors. Mess it here. So I finish with the right-hand side, saying which is this guy. which is just this term. Okay, why do I have here a vector and here I had Jx? All three directions, because here I stopped. I told you I'm switching to one of the equations for x. I return and do it for y. I return and do it for z. So I get here jx plus jy plus jz, which is what's written here. Okay. And what is this guy? We did it in the previous lecture. This ugly looking expression. Is this equal to this?
No.
Maybe by integration by parts?
I don't even need this. What's the difference here? Here I have 3 dimensions, just break it down to the problem here is that I have this combination which this guy appears here, but not this guy, right? Now I can either work with some mathematical trick or stop a moment and think about the physics. From where did this expression come? And you should have hit what's wrong here? Is this the operator of P? What
No.
is? What am I missing here?
Yeah. Minus yeah. And 12.
Right. That's why I need audience in the class, so they'll correct my mistakes. Okay. Is this guy?
Still no.
Still not. I have here half of it.
Oh, so it's a symmetry of the.
And here I have the same thing, complex conjugate.
Okay.
Right?
Yeah.
Now I stop and ask myself, what am I calculating? Momentum, right? Momentum is
Real?
it's real. It's an observable thing that I can measure. Therefore, the complex conjugate of a real number,
Is 0. Like.
no, a complex conjugate of a real number is
Oh, yeah.
definitely
It's
not zero.
It's the same.
It's the same number, right? So what I have here, this is equal to its complex conjugate. So we have it written down twice, exactly what appears here. So for any psi, what is the only property of psi that I needed here? The fact that it's normalizable. That's a probability of finding it somewhere if I integrate overall space is 1. So I have this term. Okay, so now let's go back to the problem that we defined at the beginning. And proving this part got a name. Ehrenfest law or Ehrenfest conjecture, or whatever you want to call it. So Ehrenfest had a couple of things in common with Boltzmann. One of them is that he was mainly concerned with statistical physics. Can someone guess what is the second? Both of them committed suicide. So apparently statistical physics is not good for your mental health. Anyway, why did it get such a bombastic name? It's a 3-line calculation. Because once, in the beginning, when quantum mechanics was introduced, this sounded extremely strange. People couldn't understand what are these people talking about. Wave function, statistical properties, averages, we can't get it. So people started playing with very simple examples and trying to see if they get the physics that they are all familiar and feel happy with. One of them was Ehrenfest and working on Newton's law. So that's why it got a bombastic name, although the statement is very easy to see. Okay, so I'll break it up for the x-axis, and I can go and do it also for y and z. Okay, what did I do here? Just explicitly wrote down the average. Okay, I want to pull the derivative according to time inside. What are the terms that have a derivative by time? What depends on the wave function? Excuse me? The wave function. These are the only parts of this integral that depend on time. The operator doesn't depend on time. As a glimpse into the future, which will be either one of the last, actually, usually it's pulled into quantum mechanics 2, but sometimes if we have time, we'll do it in 1. We have time. You can do a complete different formulation of quantum mechanics where the wave functions have no time dependence and the operators do have time dependence. But that's not the notation that we'll use during most of the course. But here, wave function have time dependent, operators don't have time dependence. Okay. Yeah, just pulled the derivative according to t into the integral. Okay. Where have we met derivatives of the wave function according to time? Or in another way to ask it, where have we seen something about the time dependence of the wave function?
Schrodinger's equation?
Exactly, Schrodinger's equation. So the other things that a wave function has to fulfill, except for normalizability, is that it has to follow the Schrödinger equation. Okay, let's write down the Schrödinger equation explicitly. So that's the good old Schrödinger equation. All I did is divide by IH bar. And I can check consistencies that complex conjugate of this guy is equal to this guy. Okay, I have to pull out what's written here and stick it into my integral. So, a bit long, but not terribly long. Okay, I had two terms where dou to dou t appeared, and now I have four, because each term gives me two terms. Hopefully I copied it correctly. And it looks as if I only complicated whatever I have here. What I have here actually written as an integral is dr. See it? Just changing notation. Okay, but this guy Why? Because if I do a chain derivation here, I'll get a mixed term that the minus will kill, and a squared term which is written here. And at this stage of the course, what does that scream of? Grad of some vector, right? This guy is a vector.
So false.
Current.
What?
All the guy in this squared brackets is some kind of a current.
Oh.
Right? Of these two functions. Not the current that we've met of psi and complex conjugate psi, but of derivative of psi. But if I want that my wave function will normalize over space, what do I know of its derivative at infinity?
Zero.
Zero also. No current, this guy goes to zero. So I take what's written here and forget of the first two terms. They don't contribute to the integral. So I'm left with this guy. I have enough space here. Okay. Someone has an idea how we progress with this guy? To remind you, we had the right-hand side of the equation. We had f equal ma, right? And f was grad v, and this guy was right? So we are looking at this guy. Okay, we don't have here gradient of v, but we have a derivative. Remember, we'll have the dou to dou x, which is written here, dou to dou y, dou to dou x, to dou z. Can perform here the derivative. Right?
middle of the integral at the top there should be a minus instead of a plus? And then it
yes, it's a minus. Thank you. You remember we had here because of using proved. Okay. One can play with other types of averages and prove that they are fulfilled, that are correct in classical physics, and see that we'll get it also in quantum physics. Okay, so what have we learned out of all this exercise? That at least our definition of how to pull out averages out of wave functions and how to define physical quantities using operators at least is consistent. We get classical physics out of it. Now, the last known classical properties that we'll show before moving to a refresher on linear algebra is conservation of energy. Okay. So, for what type of a Schrödinger equation do we expect conservation of energy? For any Schrödinger equation?
Complex?
Schrödinger equation is always, the wave function can't be complex. To remind you, just clean up the black.
Schrödinger's equation is conservation of energy.
No. Oh. There's a caveat, there's a point that one has to pay attention. And I'll explain, of course, nature has to conserve energy. But give me a moment and you'll see what I mean. Okay, so the Schrödinger equation right? And the only thing I'm missing is the potential. And in principle, the potential may have spatial dependence and time dependence. And if I have time dependence, Schrödinger equation doesn't conserve energy. Think about a wave, putting a particle in an electromagnetic wave. The electromagnetic wave can transfer energy to the particle. So, I have conservation of energy or a stationary potential. Now, what's the problem? We know that energy in nature is always conserved. Because if we'll think about it deeply, we are doing here some strange combination in the Schrödinger equation. We treat the particle quantum mechanically. The potential is a classical potential. Now, if we'll come and think about it as an electromagnetic potential, for example, we'll have electromagnetic waves, and if we really do quantum mechanics, we have to treat them as photons. And we need a different equation, a quantum field equation, and that will be for graduate studies. So in the form that we write down the Schrödinger equation here, energy is conserved only for a stationary potential. If you think about it, that's the same behavior that we have in classical physics. If you write down in classical physics a time-dependent potential, meaning a time-dependent force, this force can transfer energy to your particle. No conservation of energy if you ignore what's generating the force. If it's just a given, like a potential here, energy is conserved only for time independent potentials. So I'm writing here V of R, no T dependence. Okay, now we will understand why they bothered to teach you differential equations. Okay, this side of the equation, on what does it depend?
Time.
Time. This, the operator has no time dependence, only space. If you have learned anything out of your course in differential equation, what type of solution should I guess here or expect here?
Sinus?
Separation of variables. I don't know if it's a sinus because no one told me anything about V except for that it depends only on space, not on time. But that is enough to know that it's reasonable to guess a solution where we have separation of variables, meaning that we started with psi of R and T, and we can write it as some function that depends only on T, and some function which we will continue to, in order to confuse you, to call psi of R. So just any time you need jerk reaction on seeing an differential equation that has on one side only dependence on one variable and on the other only on the other variable is to write down a separation of variables and stick this solution into the equation and see what we get. Okay. I'm writing it down first time that we run into it in details. Okay, so far so good. I didn't do anything. Just wrote it down explicitly. Okay, here's the derivative according to t. This is a constant for the derivative according to t. This is a derivative according to r. Doesn't depend on time. Sorry if I'm boring you, but we'll do this trick again and again and again during the course. The first time I'm writing it down in details. The rest of the course I'll just say separation of variables, etc. Okay, what do I want to get here? I want to get here two sides of the equation, one depending only on t, one depending only on r. Okay, what am I doing here? I'll divide by simple division. One side has only dependence on t, the other side has only dependence on r. As far as we know, there are two independent variables, and therefore I can equate both sides to a constant. That's the usual trick in doing separations of variables. Okay, free to call the constant whatever I feel like. Call it E. Oh, it will be energy. But at the moment it's a constant. I don't know what it is. Okay. So I'm left with two equations, and here. Okay, how do I solve the time-dependent part for ft?
You assume e to the I
Up to constants, yes. So the solution of the top one is y. Perform the derivative and you'll get exactly what's written here. So if the potential is constant, the time dependence is only a phase. Going back to how we started the course, I told that the fact that the wave function is complex is very important. If we throw out the complex part, we lose all time dependence. So that's another demonstration of this statement. And this guy has a name, stationary Schrödinger equation. If you have a bit more of mathematical knowledge, you'll say, oh, I know what type of equation this is. That's an eigenvalue equation. Eigenvalues, linear algebra, and we'll go and look into it after the break. We'll just finish immediately after the break, we'll just calculate the average of E and show some properties of it. Take 10 minutes and then we'll move to linear algebra. The reason is, it's an eigenvector equation, eigenvalue equation. So we said something about the solution of the time-dependent part. What can we say about the solution of the stationary Schrödinger equation? Not much at the point because we didn't define V, and we'll spend some time in solving this equation with all kinds of V, from free particles, that is absence of V, till all kinds of potential wells, like a square well, and colombical potential, which is the hydrogen atom. And of course, the pet potential for all physics, harmonic potential. Okay, at time. The only thing we can say at the moment without knowing anything about the potential is that psi depends on E. Okay, trivial, but needs to be stated. So at the end of the day, for a stationary solution, this is the form of the solution. Okay, what can we learn from that? Actually, surprising, we have a few things that we can learn. One thing is the probability of finding the particle at position r and time t. Well, we defined it. Again, the only times that I'll write it in detail. This times this is 1. No time dependence. Now, you may remember what I mentioned in the previous lecture, that an electron around the nucleus of a hydrogen atom, or actually of any atom, doesn't orbit the atom if it's at a given energy. I proved it here. Can someone outline how I proved it? Anyone?
The probability doesn't change by time, so it's not dependent by time. So
Yeah, but
it's stationary.
right, we need though a statement at the beginning. The potential is constant because it's just a Coulomb potential in the hydrogen atom, and therefore the probability of finding the electron anywhere in the hydrogen atom doesn't change with time. Definitely doesn't follow this intuitive picture of some electron with an orbit, because it has the same probability at any given time to be found at some position r. Okay, next things that we can conclude here. What is average energy? Okay, back to our dictionary and definitions. An average is dr psi okay, this is the operator of energy. Okay, the only place that I have time dependence is in the phase. Derivative of this will bring IE divided by h bar down. I'll get this times this is 1. Here I remain only with E. And what is the integral? What? That's why I called the constant. Okay. Let's calculate E squared. So it's the same procedure exactly. And unless you're writing on a tablet where you can drag it down, puts square everywhere. So, give you a moment to those of you who write down everything from the beginning. You. Actually, I could do it for any n. So, I'll just write it down. Here, in general, e to the power of n is equal to e . Now let us remember what we have studied in statistics, whatever course you took on statistics. If all the moment, if the nth moment is equal to the average to the power of n, what kind of distribution is it?
Yeah.
Excuse me?
Can you say it again?
Sure. What type of distribution has the property that all the moments, the nth moment, is equal to the average to the power of n, which is exactly what we got here.
Normal one.
Excuse me? No, as I said, I just didn't hear.
Normal.
Definitely not normal.
Just one value.
Right, it has a peak, a delta function if you want, if you met or if you didn't. Just, it has a probability 1 to get the average. So basically this is conservation of energy, a wave function that has the property that all its moments statistically tell you that you have only a probability of measuring the average value. It tells you that this is not a statistical property, it's a constant. Proved here. So although everyone will tell you that quantum mechanics is a probabilistic theory, nevertheless, if I have a stationary solution, meaning that I have a potential that doesn't depend on time, my energy is not a statistical property, it's a constant. That's conservation of energy. Position can be a probability, momentum, anything, but the energy, if I don't have any time dependence in it, is a constant. But actually, it's a bit more delicate. And we'll prove it, I'll just state it here so you won't go away with the feeling that you can't have probability in energy. Energy is conserved, tells you something about the behavior of that. I can get psi of r t, which is a superposition of states. And we'll deal in details with superposition in 2 or 3 lectures, but at the moment I'm just stating that I can have a solution of the time-dependent Schrödinger equation that has this form. And this form, the energy doesn't change. And I have a fixed probability of finding the system at a given energy. One of those that take part in the superposition. Why is it a solution? Just stick it into the Schrödinger equation and see that it's a solution. Why is it a solution? A deeper reason, it's a property of the linear algebra, which we will study. Another motivation. And basically, the probabilities here don't change with time. All this will prove. Let's stop here before I'm continuing giving you statements that are meaningless because of lack of knowledge, and go and do a short refresher, about a lecture on linear algebra. Okay. Although I call it a refresher, I'm introducing different notations that you're used to. It's a notation that became universal in quantum mechanics, therefore we're using it, and we'll see in a moment. So what's a vector in linear algebra? Some sometimes write it as U. You sometimes write it as U1, U2, to UN. And in quantum mechanics, in Dirac notation, that's how we write it. Okay. U1, U2, UN, I is a complex number. We'll define addition of vectors. So far, so good. So the other side, then what's written here? What does it mean? Definition, transposed and conjugate. Scalar multiplication of two vectors.
Matrix.
No, this is not a matrix.
Single, no, a number.
That's why it's called scalar, to remind us it's a number. The usual multiplication that we are familiar with from linear algebra, just a bit different. Okay. A few properties of these definitions. UV is not equal to VU. Just because the complex value here. So what's written here? Usually in this notation, A, B, C are scalars. Multiplying a vector by a scalar, I didn't write it down, but it's trivial. A times V is equal A V1, A V2, so A Vn. So what did I do here? I multiplied vector V by A, multiplied vector W by B. Both A and B are scalars, and took the vectors that I got out of it and did a scalar multiplication, and thus you can prove yourself that it's A U V plus B U W. It's a refresher, so I don't prove every statement here, but you don't see it, go back to the definition and work with it, convince yourself. Okay, something a bit more interesting, not really. What's a scalar multiplication of U with U? Well, it must be for the zero vector. Why? Because this is basically equal to and all numbers on the right hand side have to be positive or zero.
Why? Where they have to be? Why they can't be imaginary?
By definition. Where do I have it? Here. If I replace V by U, so all of them is U1 complex times U1.
Okay.
Which is the absolute values. Okay. That's not something new.
Oh.
It's also known as the norm vector. Definition. Okay, so these are the basic properties of vectors that we need. If you'll stop for a moment and map it on what we did till now, if you replace psi of r, where r is a continuous number, by r that is discrete for some reason, so you have, so psi of r is just a vector, its normalization has to be 1, which means that the norm of a wave function has to be 1. We're still a bit unclear about discrete versus continuum, but we'll get to it. Okay. Let's say I have a set of n vectors. I call it an orthonormal set if Kroneker's delta, meaning it's equal 1 when if it would have been orthogonal, not normal, it would be here any number that is not 0 for if I equal j. And for all the others, it is. Okay, again, refresher, I don't prove all these statements. If I have a vector of some size, dimension, let's say if it has 2 components, it's dimension 2, if 3, 3, and so forth. What is the largest set that I can build that will be also normal or orthogonal? Very basic property of linear algebra.
The amount of components.
Right, the dimension. Can't build a set that is larger than the dimension. Actually, that's a definition of dimension. How many independent vectors you can get that will be orthonormal to each other. Now, if I have what does it mean complete? Size d, dimension, or n if you prefer, which we used here. Any vector of this dimension can be written as a superposition of these orthogonal vectors. And what's it called?
Base?
It's a base. That's the most important concept that you pull out from linear algebra. that you can describe any vector in your space by a base, and you're writing down the vector as, let's say I have some vector u, so it's sigma I AI and okay. Someone gives me a vector u, and I want to write it down in a given base. Think about it in simple geometry. Someone gives you a point, you want to define a vector according to some base, xyz, or some rotation of xyz, whatever you're interested in. Very simple algorithm to do it. And very easy to write down in this direct notation. So I take this definition. Okay, and multiply it by some basis vector. Why? In a moment we'll see, but I'm allowed to do it. Okay. By definition of scalar multiplications that we did 10 minutes or 20 minutes ago. Good. Person on a base. This is equal. An algorithm to write down a vector in any base, perform a scalar multiplication between all the vectors of this base with your vector, and you get the amplitudes of this vector in the new base. So life is extremely simple. Someone comes in and wants a different base, no problem. I'll write it down in the different base. Just give me the base. So I can rewrite what's written here. Just wrote the definition of A. Now, just when we want to think about something, it's the easiest to do the simplest case, and then you have here the standard. And so on and so forth. And is there something special about the space? No, it's just convenient to write down. We can work with any base. Let's, for example, do a trivial example of G equal 2. But to make it a bit less simple, it's an orthonormal base. So go for 2, this is enough. Well, I should have checked 2, 2. And the other one I can, E2, E1 is just the complex conjugate of 0, which is this. Okay, so this is the base. Okay, I don't need this. Now someone comes to me and tells me my vector is in the standard base written as if kosher vector even normalized. Check that it's equal 1. Okay, but I want to present it in this base. Okay, so what do I do? Well, I have the algorithm, I'll work with it. So, rewrite it. U is equal so what do I have to calculate?
How much of each vector you should add to get U?
Yeah, but specifically, I have here an algorithm. I have to calculate these. Here I have only 2 because I is equal from 1 to 2. These 2 scalar multiplications. Okay, let's do it. So, something that I put here on the side. I want to leave this. So, U times E1. Let's write it down in the usual notation. 1 over square root of, sorry, I transposed it, that's not okay. E1 times, okay, so it's 1 over square root of 2, 1, 1, times 1 over square root of 5, 1, 2. Okay? Go down. Is this wave function still normalized in the new bases?
No. Ah, yes, yes.
Has to be. Because the length of a vector doesn't depend on what bases I present it with, right? So anything I can do in the standard base, I can do in this strange base. Let's see, for example, let's do the normalization part, the calculation. So, so I'm forgetting about the standard base. And working now with this new base. Okay, U is equal to 3 over square root 10 of E1 plus 1 minus 1 square root of 10 E2, right? That's what I got. because it's an orthonormal basis. Normalized. So, actually, instead of writing this strange notation, and I'm back to the standard basis notation, but only here I have to remember that when I'm writing 3 over square root of 10, it's times the first basis, the first vector of the base. This is times the second vector of the base. So in general, if I'm writing down an vector 1, 0, 0, 0, 0, 0, do I know what it is? No, unless someone told me what is the base. Otherwise, I don't know what it is. Tell me the base, and I'll be able to understand what are you meaning. It only means that the first entry is times the first base vector. The second entry is times the second base vector, and so on and so forth. So nothing holy, nothing special about the usual bases. Choose whatever base you feel like. Just keep the base the same all over the calculation. You can't switch in the middle. But with whatever base you're working, as long as it's orthonormal, all the rules that you already know, it's correct even for them. Because you see here, first amplitude square, second amplitude square. That's it. Let's do something that physicists are all the time used to. Mathematicians usually don't bother about it just because it's do I have to have my bases with real numbers? No. Let's put here I. And someone can guess what I should write in the other one. Let's check, as we checked previously. Now the complex is important. I have to write it correctly. That's fine. Second one, e E2, E2 will also be fine. You can immediately see. Let's check the cross term. Kosher basis. Well, can I write down my good old vectors that I've erased here? It's still the same algorithm. Nothing changed. So I need to know E1 U. So I have 1 over square root of 5 and 1 over square root of 2. This guy, remember, complex. So E1 is 1 and minus I, 1 and 2. So we have here 1 over square root of 10, 1 minus 2I. Is it a scalar here? Huh? E2 U. Normal of U in this basis. I don't have to return to the same calculation because all I have to do is square this guy and square this guy. But remember, absolute value squared. Okay, so it's 1 minus 2I times 1 plus, this is plus and minus 2I. Divided by 10, and minus I times I. 1. So I have here 5 over 10. So that's okay. Let's write it down step by step. And the second guy is 10. 1 plus 2I times 1 minus 2I. Second calculation. Both of them give me 5 over 10. It shows a different bases, but I got different amplitudes on each of the bases, basis vectors, but the properties of the vector didn't change. As usual in physics everywhere, defining a base is just my convenience. The properties don't change. Okay. So we know everything about vectors, which I'm all the time alluding that they are wave functions. What else do I need? Operators. We'll see that operators are matrices, and that will be the next lecture.
the next